Hey kiddos, happy week 13. Today for our asynchronous class, we're going to investigate the motion of a simple pendulum. We're kind of getting into a sequence again, like I said last class, where we're looking at oscillatory motion. Okay, waves, light, sound, things along those lines. And we're going to begin that study of oscillatory motion with the study of a pendulum, a really simple thing that oscillates. And this will serve as an introduction to a type of oscillatory motion called simple harmonic motion. Your data that you collect today will eventually turn in to a lab report. It'll be something that you submit, and this should be considered the warm-up for your IA. Okay, we won't do a full lab report, but just the analysis and evaluation sections of an IB lab report. And I will post in the resources module on Canvas the full rubric for an IB lab report. But again, we're only doing the analysis and evaluation sections. All right. So let's talk about what a simple pendulum is and what it is not. Okay, a simple pendulum is one that can be considered to be a point mass. Okay, so we've got our axis of rotation right here. This is our point mass down here. And this point mass has a special name, and it's called a bob. Okay, the bob at the end of the string. It's suspended from a string or rod of negligible mass. Okay, so there has to be a string that has a mass that is much, much smaller than the mass of the bob itself. Okay, and then it'll be swinging with small amplitudes. And by small amplitudes, I mean theta, right? This angle measured relative to the vertical that the bob is displaced by has to be less than or equal to 30 degrees for this to be considered a simple pendulum. Okay. So here's our research question for the investigation we're going to take data on today. So how does the length of a simple pendulum impact the period of the swing? All right, so I ask that you take data as an individual or in your small groups. It'll be way, way more efficient if you work in your small groups, because the likelihood is high that there's at least one person in your small group that has all of the supplies needed. Okay, you're going to collect data for at least 10 different lengths of pendula, and I'll show you my setup here in a second. And you're going to copy your group's average data into a class Google Sheet on Canvas so that we can discuss the data, not just your data, but discuss the data that was collected by the whole class and see if we can come up with an additional conclusion based on the whole class data. For raw data, you'll present the data that your group collects, your at least 3 trials for your 10 different lengths. Graph your group's data and determine the line of best fit. Okay. You'll include in your line of best fit the whole class data as it becomes available. All right. One last thing I'm realizing as I'm giving you these instructions, the length of our pendulum, the length of the pendulum is from the center of the axis of rotation, not to the bob itself, but to the center of the bob. And this is often a place where there's more significant uncertainty depending on what you choose as your bob. Okay, so from the center of the axis of rotation to the center of the bob. Okay. So next class, before I show you the setup of the lab and give you some helpful hints, I want you to know what your assignment is for next class. All right, I would like you to have an IB level data table. For raw data, you should present your group's data collected, and process data will include the entire class data. So obviously, again, you'll need 3 trials at least for each of your 10 lengths. If you measure something in centimeters, right, like the length of your string, it will need to be listed that way in your raw data table. And then in the process data, those distances will then need to be converted into meters. You'll need a graph of period versus length of the class data, and then linearize your original relationship and find the uncertainty of the constant using max and min slopes. If you need help finding the uncertainty of the constant using max and min slopes using either Desmos or Logger Pro, I've posted links with tutorial videos walking you through that process in the resources section, or resources module in Canvas. Okay, and if you need help linearizing, come see me during the asynchronous class time, or some other asynchronous class time that doesn't belong to you. I don't mind. All right. Now, one of the things that you need to be thinking about and is really important when collecting data for a lab and designing an investigation when measuring period, right? The time for one full back and forth motion, one full oscillation. You need to design your experiment such that it minimizes uncertainty. Okay, if you're using a timer, your reaction time is 0.31 seconds, okay, which includes the time to start and your reaction time when stopping. Okay, you have some ability to anticipate with a pendulum, which can lower that uncertainty. But one of the ways that you can reduce uncertainty when measuring times is you can time more than one full oscillation. Because if you time, say, 3 oscillations to get the period, you divide the time by 3, and you also divide your reaction time by 3. And so that can decrease your percent uncertainty. Good data in physics has less than 30% uncertainty, and you should always try and get that uncertainty as small as possible when designing your experiment. All right, so let me show you the setup and give you some helpful hints for how you'll get your data, okay? All right, kiddos. So here are some supplies that I will suggest. So first thing you need is a string. For me, like, there was some string in my house. I was just kind of looking around the office and I found some of that like colorful ribbon that sometimes you use to wrap gifts. I've got that. I chose this roll of tape as my bob because it was easy to tie to. Just be careful when you're measuring the length of your pendulum. You're measuring from the axis of rotation to the center of the bob, right? So if I were to measure the length of the pendulum, I'd somehow have to also measure to the very empty center of this loop. Okay, I chose this. You want a bob that won't like swing around all weird or do any weird rotation on its own. It should essentially be a point mass. All right, and then I was looking around for some way to do the oscillations to get my string to stick out so it wouldn't hit like the wall or shelf or anything. First I considered a doorknob, but I didn't think my doorknob stuck out far enough. And then I tried like a golf club, but that stuck out too far. And I finally looked in my kitchen and I found this scraper, and that was really perfect. And it actually has a flat end so that I can anchor it, not by taping, but just by sticking some books on top of that flat part, and it won't rotate naturally. It'll stay put really well. Okay, so here I've got my pendulum that's swinging back and forth. All right. So again, the length of my pendulum would be from right here on the, where it starts swinging down to the center of my bob. And when I'm timing, I would time more than one back and forth oscillation, maybe like 3. So I'd start here, timing 1, 2, 3. And actually, to minimize uncertainty even more, it's hard to predict when your friend will release, but because we have the ability to anticipate, maybe you could start timing when the bob reaches its maximum on the other side. Okay, so 1, 2, 3, or something like that. All right, so 3 back and forth motions. Now you want 10 different lengths. You don't have to cut 10 individual strings. Okay, simply maybe wrap the string around your post a couple of times, and then that's a new length. All right, so 10 different lengths. They can differ just by a matter of centimeters. And remember to take 3 trials each. If you're working in your table groups, each student, if you've got at least 3 people in your group timing, 3 students timing counts as 3 trials. Easy peasy. Okay? Let me know if you have any questions, and yeah, good luck. Happy data collecting.